You're looking to quickly grasp the important developments in image editing, right? Well, today we're jumping straight into PixelHacker. It's a new technique for filling in missing parts of images, image inpainting.
Yeah, image and painting is really about making those filled-in pieces look, natural, using the visual information that's already there around the gap. And this new paper, PixelHacker, image inpainting with structural and semantic consistency, it really highlights that current approaches often, well, they struggle with complex images.
Right. They point out that getting both the structure, things like textures, shapes, how things relate spatially,
Mm,
meaning the semantics, so color consistency, restoring objects logically, getting both right, is really tough.
it is.
Looking at figure 1 in their paper, you see some clear examples. Tree trunks that look warped, railings that don't quite line up.
Yeah, or just objects that seem completely out of place, semantically inconsistent.
Even the really advanced methods right now, the ones using attention and trying to grasp context.
They still frequently produce these kinds of visual errors when the scene gets complicated. It's a persistent challenge.
Okay, so PixelHacker is their proposed solution to fix this. What's their main idea? What are they doing differently?
Well, PixelHacker is a diffusion-based model, and the core of its innovation, the really new part, is what they call latent categories guidance, or LCG. They frame it as a, let's say, a straightforward but quite effective paradigm for in-painting.
Latent Categories Guidance, LCG. Can you break that down a bit? How does it actually work?
Sure. So LCG works by constructing these image mask pairs for training. Parts of the images are masked out, hidden, and these mask areas are then broadly categorized. They're either labeled as foreground, and they mention potential for 116 categories there, or background, with about 21 potential categories.
Ah, okay. So instead of needing to know if it's a specific type of bird, it just needs to know this is something generally in the foreground. It's more about the role of the mask area.
That's really the key insight, yeah. It's
Yeah.
a broader categorization. These foreground and background concepts, they're then represented using compact fixed-size codes or embeddings, and these latent feature codes are then intermittently injected into the denoising process, the part that actually generates the filled-in pixels to guide it.
Via linear attention, the paper mentions. And this wasn't just developed quickly, I assume. There was significant training involved.
Oh, absolutely. PixelHacker was pre-trained on a really large data set. They mentioned 14 million of these image mask pairs, and then it was fine-tuned further using standard open source benchmark data sets.
14 million pairs. That's substantial. Let's talk about that data set. Where did all that data come from, and how do they specifically use it for this LCG method?
They built this data set using what they call an auto-labeling framework. It basically integrated different AI models, they mentioned AlphaClip and SAMLay, to automatically identify and categorize objects and scene elements across several large existing image datasets like Coconut Large, Object 365 V2, Google Landmark V2, plus a curated set of natural scenes.
Wow, okay. That sounds like a massive data engineering effort just to get the training material ready.
Yeah.
And the way they created the actual masks, the missing parts for the training, seems pretty important for how the model learns based on their description.
It is crucial, yes. They used 4 different types of masks, as detailed in Figure 3, and assigned each type to influence either the foreground or the background embedding. For instance, masks that covered entire objects, like masking out a bench, were assigned to the foreground embedding. The goal there is to help the model learn semantically aligned object reconstruction.
Makes sense. And what about the other mask types? What roles did they play?
Well, masks covering broader scene elements, like a patch of sky or grass, were assigned to the background embedding. This helps improve the overall semantic coherence of the background. They also used random brushstroke masks, also assigned to the background embedding, primarily to help the model focus on learning structural information like textures and edges.
Interesting. And the fourth type?
The fourth was random object masks, but these were also assigned to the background embedding. This acts as a kind of regularization, to prevent the model from overfitting too much on reconstructing specific foreground objects. It forces it to handle more varied background completions.
The paper gives some formulas for how these masks are combined. Foreground seems straightforward, just the object masks. But the background mask construction is a bit more complex.
Right. The background mask, MEG, is essentially a probabilistic combination. It takes the scene masks, adds the random brush masks based on a probability, or PRAND, and adds the random object masks based on another probability. This mix means the model learns to handle various kinds of missing information within the background context during training.
So just to recap this point,
Hmm.
even though there are potentially many specific categories for foreground, like person, car, and background, sky, road, the model isn't explicitly told these labels during training. It learns these general foreground and background concepts and the structural information implicitly through these learnable foreground and background embeddings guided by those four mask types.
That's a very significant aspect of their approach. The learning happens via adjusting the weights of these compact embeddings, not through explicit category supervision for every single type of object or scene element.
Okay, now how do these foreground and background embeddings, these LCG codes, actually influence the image generation? The paper talks about interactions between them and the image features relating to structure and semantics.
Yes, during the denoising process, which happens step by step, there are multiple interactions between these LCG embeddings and the latent features of the image being generated. Figures 2 and 4 illustrate this. Briefly, in a single interaction step, there's self-decoding using something called gated linear attention, GLA, where the image features refine themselves. And then there's cross-decoding using cross-attention, where the image features interact with the foreground and background embeddings.
So it's a kind of back and forth. The image representation refines itself, then it conceals the guidance codes, then refines itself again.
Pretty much. Self-decoding and cross-decoding alternate. And the LCG guidance, specifically the cross-decoding part with the embeddings, is incorporated after an initial cross-decoding step involving the masked input image itself.
Okay, that gives a clearer picture of the mechanism. So let's get to the results. How well does this actually perform in practice? They tested PixelHacker on some standard image datasets, right?
They did. They evaluated it on Places 2, which is mostly natural scenes, and also on CelebA-HQ and FFHQ, which are datasets of human faces.
What do the quantitative results look like on Places 2? The tables in the paper seem promising.
Yes, tables 1, 2, and 3 show the numbers. On Places 2, PixelHacker achieves state-of-the-art or highly competitive results across different metrics like FID, LPIPS, and UIDs, especially noted in Table 3 for 512 resolution where it hits SOTA. And what's quite interesting is that even the version of PixelHacker without specific fine-tuning on the Places 2 dataset already showed remarkable potential, suggesting good generalization.
That is interesting. The qualitative comparisons, Figure 5 shows some visual examples on Places 2, right?
It does. Those visuals suggest that PixelHacker does a better job compared to other leading methods at maintaining both structural integrity and semantic meaning, even when large portions of the image are masked out. The comparison methods, in contrast, tend to produce more visible artifacts, structural distortions, or sometimes just generate illogical content in the masked region.
Okay, and what about the performance on the face datasets, CelebA-HQ and FFHQ?
On CelebA-HQ, Table 4 shows PixelHacker achieving state-of-the-art quantitative performance. This indicates it generalizes well from general scenes and objects to the specific domain of human faces.
And the visuals. Figure 6, I believe.
Yes, Figure 6 shows qualitative comparisons on CelebA-HQ. PixelHacker seems to produce clearer facial features and maintain semantic consistency, like avoiding weird color discrepancies that sometimes plague other methods on faces.
And FFHQ, the other face dataset. Similar story.
Very similar. Table 5 for FFHQ again shows state-of-the-art quantitative results. This is noteworthy because FFHQ images are typically higher resolution, and the model performed well despite being trained at 512 by 512. And Figure 7 provides visual examples on FFHQ, demonstrating realistic results and good adaptability even in complex scenes with varied lighting.
The paper also includes ablation studies, where they sort of tested different components of their method in isolation. What were the main takeaways there?
Yes. One key finding from Table 6 was about the LCG masks. Using all four types, they designed the object semantic, scene semantic, random brush, and random object masks together, yielded the best overall performance compared to using subsets.
So each mask type contributes something valuable.
It seems so. They also looked at the embedding dimensions in Table 7. They found that a relatively small dimension, around 20, was actually sufficient for the foreground and background embeddings. Bigger wasn't necessarily better.
Interesting. Any other key ablations?
They also tested different guidance scales for the classifier-free guidance part of the diffusion model in Table 8. They identified an optimal scale factor of 2.0.
Right. Now, of course, no method is absolutely perfect. The paper does briefly touch upon some limitations, doesn't it?
It does, yes. Figure 9 provides some examples. They acknowledge that PixelHacker can still sometimes struggle with reproducing very fine details, particularly in small objects, or handling really intricate structures like rendering fingers perfectly. Although they also note that even in these challenging failure cases, PixelHacker often still performs better or more plausibly than the other methods they compared against.
Okay, so wrapping things up, what's the main takeaway here? What makes PixelHacker stand out as a significant development?
Well, PixelHacker really seems to represent a solid step forward in image inpainting. Its main contribution is how effectively it addresses both structural and semantic consistency simultaneously. That's been a major hurdle. Their latent categories guidance, that LCG mechanism, combined with the power of diffusion models, appears to be a very potent combination for this task.
And that massive, carefully constructed training dataset was clearly a critical factor in its success.
Absolutely. You can't overlook the impact of that 14 million paired dataset and the specific strategy behind creating those foreground background training examples using the different mask types, that the data preparation was key.
This definitely sounds like a real advancement, something that could lead to more realistic, more coherent image editing, maybe better object removal tools down the line.
It certainly pushes the boundaries there. It has the potential to make manipulated images look much more seamless and believable.
Thinking beyond just this paper then, as this kind of technology improves, this ability to deeply understand the semantics of an image and generate consistent content, what new creative possibilities might that unlock for users? What could be next?